Hello, my name is Daniel Olson, and this is a video recording portion of a results section for my project report paper for my course project for graduate computational physics, Physics 567 at Montana State University. And the reason that I have a video portion of a paper is that this project ended up being a little different from probably what's going to be a traditional course project for a course like this. I wrote a physics simulation renderer. Essentially, I made a rasterization-based renderer in OpenGL and C++ with a couple of mathematics support libraries like glim here, and it supports physics-based animation or physics simulations. Specifically, I'm modeling elasticity in objects. Due to scope restrictions over the course of the term, I'm simulating just elasticity in cubes, but it would only take another week or two, in theory, to implement that for full-on models of any kind, so not just basic 3D shapes like a cube. Um, I should note that I wrote this to use two different numerical integrators. Runge 4 is the one that I'm going to be demoing for the first couple of tests here, and then symplectic Euler is also an option for me to use. Before I go and show anything off, I should note that once I do run something, it'll open up a window that shows off the actual simulation, and behind it we have a command line window that gives off frame rate readings. We'll be discussing some of the data and the implications from those in the command line, but the more interesting thing is obviously going to be the simulations. We have three different tests for three different numbers of cubes. Numbers of cubes are 10, 7, and 4. This is just to show kind of the limits of the simulation and how it can perform. 10 cubes being something of an envelope pushing number of cubes where performance is pretty low. 7, performance is better, but still not very smooth, but it's less prone to errors of numerical integration this way. And then for 4 cubes, things run very smoothly, and you can get a really good idea of what's going on without any kind of errors that aren't inherent to this sort of programming. For the three different tests per number of cubes, we have cubes just falling, we have cubes that are meant to collide with each other in pairs, and we have random initial conditions, which the cubes kind of go any which way and may hit each other, may not. Eventually, they should come to the rest on the ground, though. So we'll go ahead and start off with 10 cubes, and here we go. All right, so you can see visually this is not very smooth. I'm capturing, or rather recording, at 60 frames per second, so that might introduce some consistency with how many frames are outputting on my screen here, but we shouldn't be getting that much more judder than we're already having for a simulation like this. So you can see the cubes have kind of come to a rest now, and scrolling through this command line output, we see that we're running at about 13 to 14 frames per second. I'm simulating or integrating 10 times per frame, so with 14 frames per second, or 13, that means that I'm integrating about 130 to 140 times per second here. And that's pretty consistent performance for tests for 10 cubes. I'll go ahead and show off what collisions might look like here. This is not the most elegant process. I didn't write a GUI or a graphical user interface for this project, just due to scope, and this was already a pretty big, ambitious project that took a lot of time, so that'll have to be forgiven here. All right. So we can see that when we're running at about this lower frame rate, we do have collisions, but they're prone to more errors than we would like them to have, namely intersection errors. So objects can come and become tangled, or their geometry intersects when they shouldn't, meaning that collision tests are happening slowly enough that something isn't getting caught, and then when it does get caught, it's already too late, something's intersecting, and you get this kind of tangled behavior like you're seeing with these cubes over here. They're kind of jiggling about, and they're giving each other forces that they shouldn't be enacting on each other. These two in particular are really not settling down because they're pretty entangled here. But this is really due to the way that frame rate and step size are tied together, as discussed in the paper. This should be a good visual demonstration, though. As you can see, we're still pretty consistently at the same frame rate. So next, I'm just going to show random initial conditions here. We'll hopefully get a chance to see collisions here too. And here we go. So we kind of see those two cubes were a good example of collision. Some of the forces they exerted made them still a little bit further than they should have. I should note also, these cubes each have a mass of about 2 kilograms. There's a bunch of different coefficients that are defined for them that I won't really go over here. But I defined this specifically so we could see some pretty springy, elastic behavior. And each one is about 4 cubic meters in size. So most of these things are falling from about 10 meters high. So that's approximately 100 feet if you're more familiar with something like a metric system. So when they take this long to fall, that's more just to show off um, the physics simulation as it's happening before things come to a pretty quick standstill. If things were falling for just a meter or two, the simulation wouldn't really have time to run long enough to fully be able to visually parse what's going on. Alrighty, so that was the 10 cube tests. We'll go ahead and switch on over to the 7 cube tests, and I'll start using Rangekata for numerical integration, and then I'll pivot to symplectic Euler just to show the kind of performance impact that we can have from using a less computationally expensive numerical integrator. We can see how simulation might differ doing that. So I have to modify another variable all the way down here. It shouldn't be too hard though. Alrighty. So this is again just cubes fall. You can see already the animation is a lot smoother. So cubes kind of come to a rest on the ground here. And we can kind of see the frame rate readings poking out here from behind the window. But we're running at about 25 frames per second for the simulation. I'm going to go ahead and get the next test running. I should change this too. This shouldn't have any impact on the simulation, but we don't want any kind of memory overflow error cropping up randomly. Alrighty. So this is the collision simulation test. You can see kind of 3 cubes here in the mid-grounds that got tangled for a little bit, but kind of bounced off of each other and interacted for a while there. This cube in particular went a bit far here, but it's coming to a rest. And I think we'll next show off the random initial conditions. And we'll go ahead and we'll change the numerical integration type. We'll change that, as I said, from Rangekata 4 to symplectic Euler. So we can see we're running at about 34 to 32 frames per second here. This cube is a pretty good example of how things sometimes get twisted up with themselves. I don't perform self-intersection tests. This is also an occasional numerical error that can happen sometimes where collision detection with the floor fails to work quite properly. This one actually is not running itself. It came to rest too early, which is unfortunate. but we can go ahead and run this again. Hopefully we should get less errors. So we have cubes kind of bouncing against each other here. And these ones don't tangle anywhere near as much. And again, we can see a readout below here, getting somewhere in the range of 32 to 34 frames per second. You can see that symplectic Euler generally is a little more poorly behaved than Runge Cut of 4, and you're seeing more intersections with the floor. But performance increases, and overall, it still looks all right. All right, next up, performance isn't really going to be impacted too much either which way. I'd rather show off with Runge Cut of 4. But let's see, where are we? Greater type. We'll change that to 0 if my mouse will let me. Go ahead and make sure that we're allocating things for OpenGL appropriately. Actually do this more efficiently this way. And we can repeat the same 3 tests and show everything off. So we'll calm down everything. We'll make sure that we're allocating different values correctly. Here we are. And let's get some vertices initialized here. Alrighty, again, we have just polling cubes. This time there's 4 of them. So we can see our frame rate readout kind of peeking out from behind the screen again. We're at about 62 to 64 frames per second. Pretty smooth motion overall. More frames are being output than is being captured here by the video recorder. You can see the system is coming to a rest. Let's go ahead and show off the second test that we have. So we can see those guys sprawling. We can see them bounce together. I'll watch as the cubes roll to a stop. Sometimes they dance a little bit like this. I had to implement the floor collisions differently to make sure that things came to a rest. Essentially amounted to setting up a normal force, and that can play around with the springs a little bit funkily. Alrighty, one final test. And this is kind of the random initial conditions. Let's take a look. All right, so this middle cube here is a pretty good example of self-intersection writing itself. And we have 2 cubes here that ended up intersecting, and we can see that even animating smoothly, once something is kind of intersecting, it can have some not great results. Thankfully, we're not getting any kind of NaN errors or anything like that, so the simulation is pretty well behaved. It doesn't blow up like a differential equation would. The cubes do have a tendency sometimes to write themselves and unintersect. I think these guys are kind of going to come to rest before them, though. Yep. So you have one that's almost leaning up against the other. All right, so that kind of shows off the project here. Comes in at about 2,500 lines of code, so it's a bit much, but yeah, I can't say I'm an artist. This is more just off the simulation quality, but that should give an idea of what it is that I wrote. The paper discusses what kind of mathematics and models were actually used for the springs and the meshes. And thank you for your time.